each of the integrals that we're going to work on today, at least to start with here, are what we call indefinite integrals. And I know we've talked about that a little bit before, but remember that an indefinite integral is one that does not have an upper or a lower limit, doesn't have any limits on it at all. Okay? And so as we start off here, before we exactly learn all the rules, whenever we do an indefinite integral, we're just looking for a function that has this integrand, this 5, as its derivative. So hopefully you can think of a function that has 5 as its derivative. What would that function be? Or a function that has that?
5x.
5x, right? And therefore, the integral of 5 should be 5x. Now, the problem, there's one small problem with that, is 5x is not the only function that has a derivative of 5. For example, doesn't 5x plus 1 have a derivative that is 5 also?
Yes.
And 5x plus 2, and 5x plus 7, and 5x minus 1,000, and 5x plus pi. They all have a derivative that's 5, right? So an important thing when we are coming up with the function that represents the indefinite integral of anything, we have to add to it a constant. And so all of these indefinite integrals will have a plus c added to them to indicate that there could be any constant added on there. So the integral of 5 could be 5x plus 1, or it could be 5x plus 2, or it could be 5x plus 1,000, or 5x plus 1,000,000, or any of those. It's 5x plus any constant. Does that make sense to everybody?
Yeah.
Cool. All right. So that is going to make our life easier now if we can, instead of just having to like go through and do these definite integrals with the limit and the summation, it's going to be a lot easier if we can just come up with a function to represent the integrals. So can you think of a function that has a derivative of 2x cubed? So we can find the integral of 2x cubed.
1/2 x to the 4th.
Yeah, 1/2 x to the 4th ought to, right? 1/2 x to the 4th, right? If you were to take the derivative of 1/2 x to the 4th using the power rule, the 4 times the 1/2 would give you the 2, and then you drop the power from x to the 4th to x to the 3rd. And we could have any constant attached to that, right? Plus 1, plus 2, plus 1,000, plus c. And in order to figure out any of these nice simple integrals of these power rule problems, we should be able to just undo the power rule. So kind of off to the side here, I want to think about this. What we do is we take our original function, which was 2x cubed, and we go, when we integrate it, we go up by a power, right? Because we ended up it to the 4th. And then we divided it by that new power. So we went to 2x to the 4th over 4. We effectively did the power rule in reverse, right? The power rule says multiply and then drop the power. So to integrate, if it's a power rule problem, you'll raise the power and then divide by the new power. Does that make sense to everybody?
Yeah.
So our power rule will be raise power by 1 and then divide by the new power. And so that will allow us to complete any of these integrals that are functions that could be dealt with using the power rule. So this integral of 1 over x to the 5th is really like an integral of x to the negative 5th, right? And is x to the negative 5th something that could be done using a power rule?
Yeah.
Yep. So what do we have to do? We have to raise the power by 1, which will make it x to the
Negative 4th.
negative 4th, and then we'll divide by negative 4. And so we'll add the constant to it. And so we would normally probably write this as negative 1 over 4x to the 4th plus a constant. But either of these answers would be perfectly fine. Everybody feel okay about that? Hopefully.
Yeah.
Okay. So what about this one? the fourth root of x cubed. Could that be rewritten so that it could be done using the power rule?
Yes.
Yeah, that's x to what power within the integral here?
3/4.
3/4. So we need to go up by 1, which will make it x to the 7/4. And then we'll divide by 7/4 and add a plus c. And this is kind of an annoying looking way to write this. So normally, if we're dividing by a fraction, we can multiply by the reciprocal. So normally we would write this as 4/7 x to the 7/4 plus a constant. Good or no?
Yeah.
Great. Anybody have any issues with any of those using the power rule? And we'll note that even this one was a power rule, right? We started with 5x to the 0 power, because that's what 5 is. It's 5x to the 0, and you raise that up to a 1, and then divide by 1, it gives you 5x. All right. Let's see if we can work through a few more of these. So the next one, tangent x over secant x dx. Anytime you are asked to find an integral of a trig expression, the first thing that you're going to want to do is try to see if you can rewrite it in a simpler form. So is there a way to rewrite tangent x over secant x in a simpler form?
Isn't that just sine?
It should just be sine, right? This is an integral of tangent, which is sine over cosine, over secant, which is 1 over cosine. The cosine should cancel, giving us an integral of sine x dx. And so I have put up in the Google Drive a list of basically all the rules for integrals that you need to know. But we should be able to figure out what the integral of sine is, because we have to try to find a function that when we take its derivative gives us sine. So what function, when you take its derivative, gives you sine?
Negative cosine.
Negative cosine, exactly. Right? Because the derivative of cosine is negative sine, so the derivative of negative cosine should be positive sine. This ought to be negative cosine x. Is this a good answer?
No.
No,
Plus
because
c.
it needs plus c. And don't forget the plus c. You might think that I will be really irritating and annoying about that and take off points, that it's unfair if I take off a point because you forget the plus c, but I can guarantee you that any calculus teacher that you might ever have in your life will take off a point if you forget the plus c on an indefinite integral. Guaranteed. So don't forget the plus c. All right, what about this next one? What should 5x cubed become?
15x squared.
That'd be a derivative.
Oh.
5/4 x to the 4th.
Yep. So we go up to x to the 4th and we divide by 4. So 5/4 x to the 4th. And then what about the cosine x? What function has a derivative of cosine?
Sine.
Sine. So the integral of cosine ought to be sine. So we just kind of got to think about these in reverse. And we add our plus c, and we're good. Make sense or no?
Yeah.
All right. What about the next one? 8t cubed. What should the 8t cubed part become?
2t to the 4th.
Right, we'll go up to 2 to the 4th and divide by 4, so that's 2t to the 4th. And then this is a 6t to the 1/2, right? So we're going to go up to t to the 3/2, right? And then we're going to divide by 3/2. dividing by 3/2 would be the same as multiplying by 2/3. So what's 6 times 2/3?
4.
4. And then this one was t to the negative 3. So if we go up from t to the negative 3, that should become a
1/4 times t to the 4th.
Up from negative 3 should be
Oh, -2.
negative 2. Yeah. And so then we'll divide by negative 2 plus our constant. And like I said, this is a fine answer. There's nothing wrong with this. Or you could rewrite this whole thing as 2t to the 4th minus 4t to the 3/2. And then minus 1/2t squared would be good too. I'd probably prefer this, but I'd take either one. Easy enough.
Yeah.
Excellent.
Oh wait, shouldn't 1/t3 be a derivative though?
I shouldn't be taking the derivative of anything. I should be taking the integral of all of these. They're all within my integral sign.
Oh, but isn't it right next to dt? Like making that, isn't that a derivative though?
The dx and the dt and the dx here are representing the infinitesimally thinness of each of the rectangles that we are summing together to find the area. These are the heights of each rectangle in the rectangular approximation. These are the widths of each of them. We sum together the height times the width to sum together all of the areas of them to get the exact area underneath this curve. That dt is not part of any of these terms in particular. It just represents the height of each, or sorry, not the height, but the width of each rectangle that we would sketch underneath this curve to approximate the area.
Wait, but then for the last one, didn't you take the derivative of cosine?
Nope, I took the integral of cosine.
Oh.
The derivative of cosine would be negative sine. The integral of cosine is sine.
Yeah, okay.
Because the derivative of sine is cosine. I'm not going to be taking any derivatives in any of these.
All right.
At least not right now. There'll be some cases where within integrals we'll have to take some derivatives, particularly in some much higher math classes, but we'll have to do a little bit of taking derivatives within integrals. So, but not yet. But that's not what that dx or that dt is. It's doing two things. One, it's indicating what the variable in here has to be. This t, this dt, has to match up with all the variables in here. This dx has to match up with all the variables in here. And it's indicating height versus width of those rectangles used to approximate the area that are infinitely being summed together. Does that make sense?
Yeah.
Okay. All right. Let's do a couple more. We got time for at least one more page here. So we're going to already start getting into some that are a little bit more complicated because the rules don't, I mean, there's not like a bunch of new rules other than learning the rules. Like, we don't have to prove a bunch of rules because we're just doing everything that we did with derivatives in reverse. Since we've proven that integrals and derivatives are inverse operations of each other. So we don't need to reprove any of these rules. We just got to be able to apply them. So we're going to get to some that are a little more difficult already. Any ideas on how we might go about doing this one? X squared minus 1 squared over x squared?
Well, we already know that the denominator is just x.
How is the denominator just x?
Because, like, yeah, the derivative of this would be like something divided by denominator squared. So then the denominator is x then, because, like, yeah.
Okay, so you're trying, I see what you're trying to do. You're trying to undo the quotient rule on it, right?
Yeah.
Yeah, so we're not going to ever have to undo the quotient rule, or in fact, even in this class, we're not going to have to undo the product rule. What we want to do right now is just get this into a nice, simple form that we can use the power rule with. So does anybody see a way we could turn this into one that we could use the power rule for?
Turn the x squared in the denominator into x to the negative 2 at the top.
All right, so if I did that, I'd have stuff being multiplied together, like an x to the negative 2 times this thing. And in order to simplify it down to use the power rule, I can't have any multiplication or division between terms. So before we can do that, we're going to want to try and simplify out this numerator. But you've got a good idea about making this x to the negative 2. That is one thing we could do once we simplify out the numerator. So I'm going to simplify out the numerator first, x to the 4th minus 2x squared plus 1 over x squared. And then we've got two options. One is we can turn this x squared in the denominator into an x to the negative 2 and distribute it through. Or the other option is we can just divide each term by x to the 2nd. And I think dividing each term by x to the 2nd is going to be a little bit easier. So we can make this the integral of x to the 4th over x squared is x squared minus 2x squared over x squared is minus 2. And 1 over x squared is x to the negative 2. Would everybody agree with that?
Yeah.
And now that's one that each piece of that can be done using the power rule. So what should that become? What does x squared become?
X cubed over 3.
Okay. What about the minus 2?
Minus x squared.
2x, right?
Yeah, minus 2x, right? Anytime it's a constant, it's just going to get an x or whatever the variable is attached to it. Because this is like having x to the 0. And so you go up to x to the 1st and divide by 1. So that'll just be minus 2x. And then what about x to the negative 2? That should go up to x to the
Negative 1.
1, and then you got to divide by negative 1.
Negative.
And then add your constant. So a good answer for this would look something like x cubed over 3 minus 2x and then minus 1 over x plus a constant. Good or no?
Good.
All right. All right, last one that we will do today. 1 over cosine u cotangent u. What should we do with that? What I say we should always do if we have a trig expression, always try to simplify it, right? Like that one before.
Sine over cosine squared.
All right, that's one thing that we could do. All right, so this would become cosine over sine, so that brings the sine up. So it would be sine x or sine u over cosine squared u du. But that's going to look a little more problematic, I think. There is a way to do this, but not using any methods that we know of yet. So this is not the best way to rewrite this. Let's see if we could try to rewrite it using or without a fraction. Can we rewrite it without using a fraction? What would 1 over cosine be?
Secant.
Secant u. And what would 1 over cotangent be?
Tangent.
So now we have secant u tangent u du. That should look very familiar.
Doesn't it make secant?
Yep, the derivative of secant is secant tangent, so the integral of secant tangent, it ought to be secant. Secant u plus a constant. Good or no?
Good.
Cool. All right, we're gonna stop right there.